Welcome! In this session, we'll explore an exciting problem titled Friends of Appropriate Ages. We'll break down the problem, discuss various approaches, and analyze their efficiency. Let's dive in. The problem Friends of Appropriate Ages revolves around determining how many friend requests are sent within a social network based on a set of rules. Each person is represented by their age, and there are three key conditions that dictate whether a person X will not send a friend request to another person Y. First, if Y's age is less than or equal to half of X's age plus 7, no request is sent. Second, if Y's age is greater than X's age, a request is also not sent. Finally, if Y's age is greater than 100 while X's age is less than 100, X won't send a request. If none of these conditions are true, person X will send exactly one friend request to person Y. Given an array of ages, where each age corresponds to a person, the task is to calculate the total number of friend requests sent based on these rules. The input is the array of ages, and the output is the total count of requests. To better understand the rules, let's look at some examples. In the first example, the input is ages equals 16, 16. Here, we have two people, both aged 16. According to the rules, the conditions for not sending a request do not apply. Person 1 can send a request to person 2, and person 2 can send a request to person 1. This results in a total of 2 friend requests sent. It's a simple scenario where both individuals are of the same age and meet the requirements to send requests to each other. This demonstrates how the rules are applied and how we count valid requests in a straightforward case. In the second example, we have ages equals 16, 17, 18. Here, we see 3 individuals with slightly different ages. Based on the rules, person 2, who is 17 years old, can send a friend request to person 1, who is 16. Similarly, person 3, aged 18, can send a friend request to person 2, aged 17. However, no other combinations satisfy the conditions. For instance, person 1 cannot send a request to person 2 because the age difference violates the first condition. Adding up the valid requests, we get a total of 2 friend requests sent in this example. Now, let's look at a more complex case with ages equals 20, 30, 100, 110, 120. Here, we have 5 individuals with a wide range of ages. The valid pairs are as follows. Person 3, aged 100, can send a request to person 4, aged 110, and vice versa. Additionally, person 5, aged 120, can send a friend request to person 4, aged 110. Other pairs do not satisfy the conditions. For example, person 1 cannot send a request to person 2 because their age difference violates the rules. Summing the valid requests, we get a total of 3 friend requests sent. It's important to carefully consider the age conditions for each pair, especially when there are large age differences or ages near the boundaries of the rules. To start, let's discuss the brute force approach. The intuition here is straightforward. For every person in the dataset, we compare them with every other person to check if a friend request can be sent. The conditions for a valid friend request are clearly defined. First, the recipient's age must be greater than half the sender's age plus 7. Second, the recipient's age must be less than or equal to the sender's age. Finally, depending on the problem constraints, we also check if either age exceeds 100. To implement this, we use nested loops to evaluate all pairs of individuals and count how many satisfy these conditions. However, this approach has significant drawbacks. The time complexity is n squared, as we are comparing every pair of people, making it computationally expensive when the input size becomes large. For instance, if the number of people approaches 10,000, this approach becomes impractical. Additionally, it doesn't require extra memory, which keeps the space complexity at 1, but the inefficiency in time is the primary concern with this method. Now, we move to a more efficient solution, the optimized counting approach. The key insight here is that the range of ages is limited, from 1 to 120, which allows us to use a frequency array to count how many people fall into each age group. With this setup, instead of comparing every pair, we can calculate valid friend requests by iterating over all possible age pairs systematically. For each pair of ages, we verify if the conditions are satisfied. The recipient's age must be greater than half the sender's age plus 7, and at the same time, less than or equal to the sender's age. By using the frequency counts, we multiply the number of people in each age group to determine the total valid requests between those groups. Special care is taken to handle cases where both people are of the same age to avoid double counting. This approach has a time complexity of O, a squared plus n, where a is the age range, which is constant at 120, and n is the number of people. The space complexity is O, a, for the frequency array. This method is much faster for large datasets as it leverages the fixed age range, drastically reducing redundant comparisons. The chosen strategy for solving this problem is the optimized counting approach. The breakthrough realization here was that the bounded age range allowed us to use a frequency array, which eliminates the need for nested loops over all individuals. This drastically reduces the computational overhead and makes the solution scalable, even for large inputs. Compared to the brute force approach, which has a time complexity of O, n squared, the optimized approach achieves O, a squared plus n, making it significantly faster in practice. While it introduces a small additional space requirement of O, a, this is negligible because the age range is limited to 120. Additionally, it requires careful handling of certain edge cases, like avoiding double counting when two people are the same age, but this added complexity is manageable. Overall, this approach strikes the right balance between efficiency and simplicity, taking full advantage of the problem's constraints to deliver a solution that is both performant and easy to implement. In this problem, we need to determine the total number of valid friend requests that can be sent based on specific age-related criteria. Every person in the input array age is represented by their age. To determine if one person can send a friend request to another, three main conditions must be met. First, the recipient's age must be greater than half the sender's age plus 7. Second, the recipient's age must be less than or equal to the sender's age, ensuring that people don't send requests to those significantly older than themselves. Lastly, there is an optional condition that checks if either person's age exceeds 100, depending on the problem's constraints. The goal is to calculate the total number of valid friend requests for all possible pairs of individuals. To begin solving this, we can use a brute force approach. This involves iterating through every pair of individuals in the array and applying these conditions step by step, which ensures we count all valid requests comprehensively. To implement the brute force approach, we begin by comparing every possible pair of individuals in the given age array. For each pair, x, y, we evaluate the three conditions mentioned earlier. If all conditions are satisfied, we increment a counter to keep track of the valid friend requests. Additionally, we need to handle a few edge cases. For example, if x and y are the same index, we skip that pair because a person cannot send a friend request to themselves. Another edge case involves invalid age values, such as negative or 0, which should also be ignored. Lastly, for large age values, such as those exceeding 100, we ensure they are processed correctly based on the third condition. Once all pairs have been evaluated, the counter will hold the total number of valid friend requests, which we then return as the final result. The brute force approach, while straightforward, has a significant limitation in terms of efficiency. With two nested loops, the time complexity is O, n squared, which becomes impractical for large arrays, especially when n exceeds 10,000. However, there are some key insights that can help us optimize this process. First, the conditions exhibit symmetry. For example, if person X can send a friend request to person Y, it might also be possible for Y to send one to X. This symmetry can be leveraged to reduce redundant computations. Additionally, the conditions define a specific range of ages for valid friend requests. For each person, the lower bound is determined by the formula 0.5 * age x plus 7, while the upper bound is simply their own age. Recognizing this range constraint allows us to narrow down potential recipients more efficiently. Finally, by using auxiliary data structures such as a frequency counter, we can perform range-based queries faster, avoiding the need to compare every pair individually. To better understand the brute force approach, let's walk through an example with the array age equals 20, 30, 100, 110, 120. Starting with the first person, who is 20 years old, we check all other individuals to see if they satisfy the conditions for a valid friend request. None of the comparisons result in valid requests because the minimum required age for a recipient is approximately 20.5, which disqualifies everyone. For the second person, age 30, we again compare them with all others. In this case, the condition age, y, equals 30 narrows the options, and we find that 30 satisfies the criteria, though self-pairs are excluded. Repeating this process for all individuals, we calculate the total number of valid friend requests. To optimize this brute force approach, we can sort the array to streamline comparisons and use a sliding window to identify valid age ranges more efficiently. Another option is to use a frequency-based approach, where we count occurrences of each age and perform quick range queries, reducing the overall computation time. Finally, let's analyze the complexity of the algorithm. The brute force method, with its nested loops, has a time complexity of n squared. This is manageable for small inputs but becomes infeasible for larger arrays. Optimizations like sorting and using a sliding window can reduce this to n log n, by limiting unnecessary comparisons. Alternatively, a frequency-based approach that leverages age counts allows us to achieve linear time complexity, n, for range queries. As for space complexity, the brute force method requires no extra space beyond the input array, making it 1. Optimized methods, however, may require additional space, such as n, for the frequency array. Overall, these optimizations make the solution scalable for larger datasets, ensuring both efficiency and correctness. This solution addresses the problem of determining the number of valid friend requests based on specific age constraints. Here's the breakdown. 1. Initialization. We use the counter class from the collections module to count the frequency of each age. This allows us to efficiently calculate the number of people at each age, which is essential for determining valid friend requests. 2. Nested loops. The outer loop iterates over all unique ages, age_x, and the inner loop checks all possible ages, age_y, that age_x can send friend requests to. This ensures we evaluate all age pairs for valid requests. 3. Friend request conditions. The conditions specified in the problem are checked. Age_y less than or equal to 0.5 *age_x plus 7. This ensures age_y is not too young relative to age_x. Age_y age_x. This ensures age_y is not older than age_x. Age_y greater than 100 and age_x 100. This prevents unrealistic scenarios where an older person requests a younger one. 4. Counting requests. If age_x equals age_y, we calculate the number of friend requests using the formula age_count, age_x, asterisk, age_count, age_x, 1. This handles the case where individuals of the same age can send requests to each other. For different ages, the number of requests is calculated as age_count, age_x, asterisk age_count, age_y. 5. Output the result. The total count of friend requests is returned as the final result. This solution is efficient due to the use of the counter for age frequency and the constrained nested loop that avoids unnecessary computations. The runtime complexity is approximately n squared in the worst case, but the constraints make it feasible for practical use cases. Here, we begin by importing the necessary utilities and defining our solution class. The method numberFriendRequests is tasked with calculating the total number of friend requests based on the given rules for appropriate ages. First, we initialize an array age count to track the frequency of each age, since ages can range from 1 to 120. We iterate through the input array ages and increment the corresponding index in age count to build this frequency map. Next, we initialize a variable friend requests to store the total count of valid friend requests. Now, we use a nested loop to iterate over all possible age pairs, represented as agex and agey. For each pair, we check if the friend request conditions are satisfied. For example, the first condition ensures that agey is greater than half of agex plus 7, following the age rule. If this condition fails, we skip to the next pair. Similarly, we check if agey exceeds agex, or if agey is greater than 100 while agex is less than 100. If any of these conditions are violated, we continue to the next iteration. Once these conditions are validated, we calculate the number of friend requests that can be sent based on the age pair. If agex and agey are the same, we calculate the friend requests as age count, agex, asterisk, age count, agex, 1. This accounts for the fact that a person cannot send a request to themselves, so we subtract 1 before multiplying. On the other hand, if age x and age y are different, we calculate the friend requests as age count, age x, asterisk age count, age y, which simply multiplies the number of people with age x by the number of people with age y. These calculations are added to our friend requests variable, and the nested loop continues to evaluate all possible age pairs. Finally, after all iterations are complete, we return friend requests, which holds the total number of valid friend requests that satisfy the given conditions. This implementation efficiently handles the problem by leveraging a frequency map and carefully adhering to the rules for appropriate ages. In the problem friends of appropriate ages, we need to determine how many friend requests are sent between people based on their ages, following specific conditions. These include rules like a person only sending requests to others within a permissible age range, derived from the formula 0.5 age_x plus 7, and ensuring they don't send requests to those older than themselves or to individuals over 100 if they are under 100. Additionally, self-requests are only allowed when there are multiple people of the same age. For example, given the input 16, 16, 17, 18, we start by creating a frequency count of the ages using the counter class, resulting in age_count equals counter, 16, 2, 17, 1, 18, 1. Then, we initialize a variable friend_requests equals 0 and iterate through all unique age pairs, age_x, age_y, to evaluate them against the given conditions. Let's begin with the first pair, where both ages are 16. For the pair where age_x equals 16 and age_y equals 16, we check the conditions. First, age_y less than or equal to 0.5 asterisk age_x plus 7 evaluates to 16 equals 15, which is false. Next, age_y age_x evaluates to 16 16, which is also false. Finally, age_y greater than 100 and age_x 100 is false as well. This makes the pair valid. Since age_x equals age_y, the number of requests is calculated as age_count, 16, asterisk, age_count, 16, 1, is equal to 2 times 1 equals 2. Moving on to age_x equals 16 and age_y equals 17, the condition age_y less than or equal to 0.5 asterisk age_x plus 7 evaluates to 17 equals 15, which is false, but age_y age_x evaluates to 17 16, which is true, causing us to skip this pair. Similarly, for age_x equals 16 and age_y equals 18, age_y less than or equal to 0.5 asterisk age_x plus 7 is false, but age_y age_x is true, so we skip this pair too. Repeating this process for all other pairs, the total number of requests for this example is 2. In another example, with the input 20, 30, 100, 110, 120, we again start by counting the ages, resulting in age_count equals counter, 20, 1, 30, 1, 100, 1, 110, 1, 120, 1. For age_x equals 20, we evaluate all possible age_y values from 20 to 120. However, all pairs fail the condition age_y less than or equal to 0.5 asterisk age_x plus 7, since the threshold here is 17. Next, for age_x equals 30 and age_y equals 30, the pair is valid because it satisfies all conditions. However, since there's only one person of age 30, the requests are calculated as 1 asterisk, 1 to 1 equals 0. For age_x equals 100 and age_y equals 110, the condition age_y greater than 100 and age_x 100 is true, so we skip this pair. After evaluating all pairs, the total number of friend requests for this example is 0. In the final example, with the input 101, 102, 103, 104, we count the ages and get age_count equals counter, 101, 1, 102, 1, 103, 1, 104, 1. For age_x equals 101, we evaluate pairs with age_y ranging from 101 to 104. Since all conditions are satisfied for age_y equals age_x, each pair contributes 1*1 friend request. Summing up the requests for all valid pairs results in a total of 6 friend requests for this example. The key insight here is that by using nested loops to evaluate all possible age pairs and applying the friend request conditions, we can systematically calculate the total requests. Additionally, leveraging the counter class helps efficiently handle groups of the same age, avoiding redundant computations. To analyze the time complexity of our solution, we start by examining the nested loop structure that iterates over the frequency dictionary age_count. This dictionary represents the frequency of each unique age in the input list ages. The outer loop iterates through all unique ages, which we denote as m. For each unique age_x, the inner loop also iterates over all m unique ages. This nested loop results in m*m iterations in total, or O, m squared. Within these loops, the operations to check the friend request conditions are constant time, as the if statements involve simple logical comparisons. Similarly, the calculation for the number of friend requests, which involves basic arithmetic operations like multiplication and subtraction, is also O1. Now, since m represents the number of unique ages and in the worst case, all ages are distinct, m equals the length of the input n. Therefore, the overall time complexity in the worst case is O, m squared, which simplifies to O, n squared. Now let's consider the space complexity. The primary contributor to the space usage is the frequency dictionary, age_count. This dictionary stores one entry for each unique age. In the worst case, where all ages are distinct, the dictionary will have m entries. However, since the range of possible ages is bounded, for example, between 1 and 120, the maximum size of this dictionary is a constant, denoted as k. This means the space required for age_count is O, k. Additionally, the algorithm uses a few variables like friend_requests, age_x, and age_y, which require constant space, O1. Combining these, the total space complexity is O, k. Since k is a small constant due to the bounded age range, the space complexity is effectively O1 for this problem. Let's compare the current optimized approach to a brute force method. A naive solution would involve iterating through all pairs of people to check the friend request conditions. This approach would require O, n squared, iterations for n people, leading to a time complexity of O, n squared. However, the space complexity of this brute force approach would be O1, as it doesn't rely on additional data structures. In contrast, the optimized solution improves performance by grouping people of the same age using the counter data structure. This eliminates redundant checks for pairs of people with the same age and allows efficient counting. While the worst-case time complexity still remains O, n squared, the optimized solution is significantly faster in cases where the input contains many duplicate ages. The space complexity is O, k, which is constant for a bounded range of possible ages. Considering different scenarios, the best case occurs when there is only one unique age in the input, making m equals 1 and the time complexity O1. In the average case, if the input has a moderate number of unique ages, the time complexity becomes O, m squared, where m is generally much smaller than n. Finally, in the worst case, where all ages are unique, m equals n and the time complexity is O, n squared. To formally justify the time and space complexity, let's break it down mathematically. The nested loop structure results in O, m squared, iterations, as the outer and inner loops each iterate over all m unique ages. Each iteration of the loop performs constant time operations, such as checking conditions and computing the number of friend requests. This confirms that the overall time complexity is O, m squared. In the worst case, where every age is unique, m equals n, and the time complexity simplifies to O, n squared. For the space complexity, the counter data structure dominates, requiring space proportional to the number of unique ages, which is O, k. Since the range of ages is bounded, k is a constant, reducing the space complexity to O1. This analysis solidifies our understanding of the algorithm's efficiency in terms of both time and space. When solving this problem, there are several common mistakes that can lead to incorrect or inefficient solutions. First, many people overlook edge cases, such as when age x or age y is less than or equal to 14. This can cause issues because the constraint age, y, greater than 0.5 age, x, plus 7 must always be carefully validated to avoid miscalculations. Another frequent issue is checking the conditions in the wrong order. For example, if you evaluate age, y, equals age, x, before confirming that age, y, greater than 0.5 age, x, plus 7, you might perform unnecessary computations or end up with incorrect results. Over-relying on the brute force approach can also be problematic. While it might work for small inputs, an n² solution will likely exceed time limits for larger datasets. Instead, optimized techniques like sorting or using prefix sums are essential. Additionally, failing to handle duplicate ages efficiently can result in redundant calculations. For instance, if several people are the same age, you don't need to recompute friend requests for each individual. A frequency table or hash map can help eliminate this redundancy. Finally, even when using optimized approaches like two-pointers or binary search, implementation errors are common. Off-by-one mistakes or incorrectly updated pointers can lead to infinite loops or boundary issues, so handling these carefully is crucial. Now, when approaching this problem in an interview setting, there are some key strategies to keep in mind. Recognizing the underlying pattern is crucial. This problem is essentially a range-based counting problem, and identifying how the constraints translate into specific ranges is the first step toward optimization. Techniques like sorting, combined with two-pointer or binary search strategies, are often the most efficient way to solve range queries. It's important to understand the trade-offs of these methods, such as the added complexity of managing pointers versus the reduction in overall computation time. Interviewers often emphasize edge cases, so make sure to practice identifying scenarios like the smallest or largest ages, multiple people with the same age, or cases where no friend requests are valid. Demonstrating your ability to handle these gracefully is key to impressing your interviewer. Additionally, discussing spacetime trade-offs shows a deeper understanding of algorithm design. For instance, using hash maps or arrays for frequency tables might increase memory usage but can significantly reduce redundant calculations. Finally, this problem is closely related to other LeetCode problems, such as threesome closest, valid triangle number, threesome smaller, and twosome less than k. These problems also involve range-based logic and often rely on similar optimization techniques like sorting and two-pointers, so practicing them can strengthen your skills for this type of question. There are also some alternative approaches to consider for solving this problem effectively. One popular method is to sort the ages and use a two-pointer approach to count valid friend requests. This reduces the complexity to n log n for sorting, followed by n for the two-pointer traversal. However, sorting does add extra space and time overhead, so it's important to weigh this trade-off against the simplicity it brings to range-based calculations. Another efficient method is to use binary search after sorting. For each person, you can quickly locate the range of ages that satisfy the constraints using binary search, which ensures an overall complexity of n log n. However, implementing binary search requires careful handling of edge cases to ensure indices are updated properly and that no valid pairs are missed. A third approach involves leveraging a frequency table. By counting occurrences of each age, you can pre-compute valid friend requests in n, eliminating redundant calculations for duplicate ages. While this method is highly efficient in terms of computation, it does require additional memory for the frequency table. Understanding these trade-offs will help you decide which approach is best suited for the input size and constraints of your specific problem instance. Great job! To recap, we tackled the friends of appropriate ages problem, analyzed a brute force approach, and discussed key takeaways. Keep practicing, and be sure to engage with our content for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!